This is the radiation. So basically, you all know what is meant by the alpha, beta, and the gamma particle. So alpha is nothing but helium. Helium-24. Is it helium-24? Then what is helium? Known to electron. So it's an ionized form of helium is alpha. And what about beta? Beta is electron to positron. It's equivalent to electron. But this forms only when the transition of one nucleon converting into other. So, and the gamma is excited nuclei will come to the ground state by releasing this energy. So let's say X is an element ZA, and then by emitting alpha particle, then what will happen? For this one, there is a reduction of atomic number by 2, and this one A by 2 or 4. 4 or 2. Ichi plus, okay, some Q will be there, some energy. Okay. And for example, X, Z, A, by releasing beta, then what will happen? So X will be Z plus or Z minus? Z plus 1? Same. And then X, Z, A, positron comes in. Then Z minus 1, same thing. And then X, Z, A star will become X, Z, A by this now. So this is what the conversion. If it is electron capture, so that means E minus 1 plus X Z A. This will become X Z plus 1. Let's see. The electron capture, what will happen is goes to Z minus 1 again times E. So when it captures an electron, also it changes. Okay. So these are the stars, and at the nuclear level, let's say one neutron converting to proton, it produces an electron plus and P2. So why this is coming? Because it's a charge balancing, charge conservation, based on the conservation. So if you do this way, then there is the conservation is missing some aspects. Okay. In order to satisfy the conservation class, conservation in respect to mass, energy, spin, isospin, there are a lot of angular momentum. So a lot of stuff are there. Based on whether it is a kind of what kind of interaction. There are 4 types of interactions. One is a strong interaction, and then weak interaction, electromagnetic. So these are the major 3 interactions. Okay. If it is a strong interaction or any of these, so the spin quantum numbers must satisfy. So for that, it is being introduced newly. Okay. And if it is the same kind of when proton convert into neutron, it produces a positron plus nu. The nu is the elementary particle, kind of neutrino, massless, chargeless, neutrino, and this one is positron, so positive charge of an electron. And this is same as electron, that is what we know, the electron that outer shell. Yeah.
So mass
mass conservation area. Neutron mass what is? Yeah.
So it's first okay. Second is
Second one is
total mass கம்மி
so there is let's say the reaction is this variable or The Gildu converts out will convert in terms of energy. Okay, the mass defect will convert into the energy. But there will be a conservation for sure. This reaction is correct. It happens, but the excess or the mass will be like kind of. Generally, this is what happens most of the cases. Neutron. But there is a chance that proton also get converted to neutron by releasing this possible. Okay. So positrons will minus, this ones are plus. Yeah. Okay. So this is one thing, and this the beta decay. So there is something called allowed beta decay and forbidden beta decay. Okay. So the allowed beta decay is something like you must have known this. Have you studied this allowed beta decay in terms of angular momentum point of view? L value. So if not, we'll just give the classification. So the allowed beta decay, L equal to 0 emission. L equal to 0 is called S-wave. So this S-wave emission is allowed. Allowed beta decay. So that means your L value is 0. Okay. And the parity is associated with the parity, L equal to 0 means it's 1. Okay. Even or 1. Now, the forbidden one, so thus parity pi equal to minus 1 over L or plus 1. That means no parity change during this process. So, suppose when beta is being released, the parity is not changing, even as long as it's allowed. And there are forbidden transitions. And the forbidden transition that depends on, let's say, the parity will flip. Flips based on L value. For example, this is a comparison. The type of beta decay. So the type of beta decay, and then so let's say L value, and then parity change. Suppose this beta decay is allowed. Your L value is, let's say 0, to be small points, and then there is no parity change. And then first forbidden. The L value is 1. Basically, is L equal to 1 stands for it's a P wave. Basically, the P orbital. So, because L equal to 1, parity changes this. Because minus 1 over L. So, parity will change. Okay. And similarly, the second forbidden. Basically, it's a D wave. And this will be 2, and there will be no change. So that means whenever you have odd number of forbiddens, so then your L value will become odd number, then parity will change in the beta decay process. Okay. So for that there is one, let's say, the nucleus, the 25, problem number 25 and 45. So basically they are related. Let's put this 20. So the 25th problem, the nucleus X undergoes a first forbidden beta decay to any place Y. So from X to Y by releasing first forbidden beta decay. If the angular momentum I and the parity denotes let's say 7 by 2 for 7 by 2 minus for x. That is j or I to the power of t. So your I or p or the morning session, whatever you are saying, in this problem they have mentioned like I and the p. I for angular momentum, p for parity. So if you are confused, you can use this. But in the exam point of view, it is given that. So because every year the question paper is different. So I and p value is this, and I and p value for y. So that is the question. So how will you do this selection group? Is the parity sign is changed or not? It will change because of forbidden. First forbidden. And therefore parity, the options are, let's say 1 by 2 plus 1 by 2 minus 3 by 2 plus 3 by 2 minus. Okay. So therefore let's say the z equal to so basically this neutron can be proton plus electron plus and neutrino. Okay, so this is what happens, and in terms of x, x z a goes to, let's say y z plus 1 into a plus electron plus neutrino. So the selection rule for delta j. So delta j can be 0, plus minus 1, plus minus 2, and so on. If it is a first coordinate, delta j change will be plus or minus 1. So then there will just be like, let's say, so for first coordinate, delta j equal to 0 plus or minus 1. So the possible value of j will be from 7 by 2 plus minus, either plus let's say if it is plus or minus 1, let's say if it is plus 1 so 7 by 2 plus 1 to 7 by 2 minus 1 more or less. This value 2 ones are 2 plus 7 9 by 2 and 2 1 2 5 by 2. So it's like just a bit like confirm with these moves. Okay. So the selection rule for the first formula 0 plus or minus 1 plus or minus 2. And there is a second forbidden. Let's say second forbidden. The selection rules are, let's say, excluding 0 for the second forbidden, delta j equal to plus or minus 2 plus or minus 3. So if we include this, so plus or minus 2, let's put this is 2 and then minus 2, then this become 11 by 2 to, let's say 2 2s are 4, even in steps of 1, so therefore you have 11 by 2, 9 by 2, 7 by 2, 5 by 2, 3 by 2. And the parity must change. If the initial parity is somewhere, that is that parity value 7 by 2, and this should be all plus. So these are all the possible states. So for the first forbidden, this is the selection rule. For second forbidden, this is the selection rule. And the parity must change, and then as per this number. Okay. So therefore, from the given option, the value is 3 by 2 is the answer. If the value is not given as let's say 9 by 2, 11 by 2, still you can use one of them. Okay. So similarly, the 45th one. So the 45th is mass the order. Is that clear? What is the condition you are supposed to do? I was being confused with whether it is a plus or minus 1 itself or included plus or minus 1. But it is included for the first forbidden. If you ask why, I have no answer. This is the condition. Yeah. Now let's say if it is allowed, for the allowed case, I said for the allowed case for the beta L equal to 0. What about the delta j? 0 plus or minus 1. So your delta j is supposed to be 0 plus or minus 1. So this is the condition. First forbidden, include this. Second, plus or minus 2 plus or minus. The moment you add here 2 and 3, what will happen is in steps of 1 you are moving, you include even plus minus 1 also. Okay. So that's the point. Okay. So the 45th problem is match. What fifth problem is match the order of beta decay given in the left column to the appropriate class in the right column. Here x, I pi and y, I pi are the nuclei with the intrinsic spin and parity. So I is intrinsic spin, pi is the parity value. So the first option is, let's say, x 1 by 2 plus goes to y 1 by 2 plus. So let's say this is 1 and then this 1 is first forbidden. Number 2, so let's say x 1 by 2 minus goes to y 5 by 2 plus. Number 2, second forbidden, let's say beta d. And the third option, x 3 plus goes to y 0 plus. And the third option is, let's say, third forbidden, beta decay. And the fourth one, x4 minus goes to y0 plus. The fourth one is allow beta d. So from this example, from this condition that we give, so can you identify, can you match which option is correct? So one goes to 4, one goes to 3, whatever the combination might be given the answer. So now let's look at one by one. So let's say x half plus goes to y half plus. Okay. So your delta j equal to 0. And the parity sign? No change. No change in parity. That means it's allowed beta. So 1 goes to 4. And what about the second one? Your x, your delta j value equal to 1 by 2 and 5 by 2. So what is the change? So 5 by 2 minus 1 by 2 is 2. So plus 2. Either plus or minus 2 you can say. If you subtract from here to here, minus 2. If you subtract from there to here, it's a plus 2. So plus or minus 2. And the parity change. Parity changes. And it can be first formula. Isn't it? You can ask a question if it is for the second also plus minus 2 is there. But the should not be, parity should not change. But here parity changes. So therefore it is a first. And then third one similarly can you work out? Second or third? Second, because there is no change in parity. And what about this one? This is third first. Because the delta j is what? 4. So if it goes to third, it will be 1 more. Plus or minus 1. Is that clear? Okay. And now another one, the 49th question. It's very straightforward from so let Ne and Pe be the kinetic energy. So the number and kinetic energy of electrons in beta decay. Which one of the following description is correct? I believe you can answer this. So question number 49. So your Ne is plotted as a function of P. P is the kinetic energy of a beta decay. So what is the relation? You all current MSc students definitely would have studied this picture. So there are 4 options. One is like these. And let's see whether you will be able to appreciate what is the meaning of this.
So 3 sir.
So let's understand what is the meaning of each term. You are saying which one is this. Let's put this A, this is B, this is C, and then D. So which one you are trying to say? C. So C is the answer. That is true, but how do you understand? When you say Ne and kinetic energy, what does this graph say? Yes, unique kinetic energy, kind of delta function. All the electrons that are coming out, the same energy. It is not possible. It's an ideal case. This one is a Gaussian distribution. There is a wide range of energy values. Okay? And then this is increasing. Kinetic energy is keep increasing, and number of beta particle also increasing with the higher kinetic energy. But when in the beta decay, actually what happens is this curve suggests that initially there is a raise in the number of particles with kinetic energy increasing. But the highest, the topmost maximum speed of electrons is very, very less number. So this, when you come here, maximum kinetic energy. So at this point, the number is almost 1 or 2. Very few number of beta particle have a maximum kinetic energy. So that is the meaning of this. And if it is the same thing for positron, so please think about it. I will give it to you. Okay. Okay. So with beta decay, we have seen that one more interesting problem. Let's discuss this. And in the morning, we are discussing about the latest coupling and other stuff. And the perfect problem, that is on 33. Can I erase this? Is it the 43rd is also in line with this? Have you discussed this 43? 43 in the morning also we did not discuss. We did not discuss right 43. Okay. Assume that N7. Assume that N730 undergoes first forbidden beta plus decay from its ground state with the spin parity Ji pi to Jf pi. The possible value of Ji pi and Jf pi. So let's say so for a beta particle, let's say for N713, and it goes to, let's say, when it is a beta plus, what will happen? Your Z will decrease basically. It become carbon and then 30 plus E plus mu E. Okay? So basically the proton convert into neutron. So therefore your Z equal to 7 for N730 and neutron number equal to 6.
So AC.
Easy?
Offering.
So is it quite often? So your N is this and this basically only one proton which is unpaired. So the spin value of this one, if it is 7, what is the spin value? Because we need to find out the spin and parity value. The spin value of initial, the morning we discuss a lot. 1p up, very good. 1p up. And the parity? Odd parity. Is that? Minus 1. So that means the spin and parity Ji pi value 1 by 2 minus. And what about the Jf? You have a carbon 6, 13, and your Z equal to 6 and N equal to 7. Is it? So the neutron will go into again P1 1 by 2. And the parity again minus 1. And J of pi will be equal to 1 by 2 minus. So both of them are 1 by 2 minus 1 by 2. So that means it's a What kind of transition?
First forbidden.
Forbidden. So what are the possible values? Okay. Then anything else that we missed in the morning session? GFDR, binding energy. Yeah. So all the problems are discussed from this point of view. Now, okay. So there is in the beta decay process. So let's say there is some classification. So the classifications are, let's say. So what we discussed in the beta decay process, where the Z number increases. Okay. If it is a positive number, decreases. Z number increases, and there are allowed first forbidden, second forbidden, third, fourth, and so on. The change in delta J and the parity, how it changes. Okay, and then there is some kind of Fermi transition. Because this is a Fermi transition, and then Gamow Taylor. So I believe GAMOW Gamow Taylor GT transition. So maybe in the question paper you can check this spelling, but the delta J, whenever it's zero, it's called a Fermi transition, and then the parity change, which is no parity change, and the 0 plus or minus 1, and the parity changes, then you call this is Gamow Taylor. Okay. Why the parity is changing when the orbital is moving? Because the orbit is with respect to spatial part. So the parity is coming from, so let's say r goes to minus r. So the negative side of the spatial coordinate. So the L will become, instead of left circular, now will become right circular. So that's why the parity plays an important role. The spin value we know, but what is the parity suggests the direction in which it is. Okay. So now the 17th problem. So let's say in the beta decay process, a transition, which is 17th problem. 2 plus goes to 3 plus. So it's allowed both Fermi and Gamow transition selection rule. Let's say Fermi Gamow selection rule. And then option B, allowed Fermi transition but not GT selection rule. Option C, not allowed by Fermi but allowed by Gamow. And D, not allowed both by Fermi and Gamow. C. So 2 to 3. 2 to 3. Del J is plus or minus 1. No parity change. So then no parity change. So actually this, let's say the condition is, I'm sorry for that. So then it is like F is not allowed. Gamow Taylor is yes. So that is the option. Okay. So again the problem number 1, there are 4 options. So let's say the basic process underlying the neutron beta decay processes. The neutron beta. The very first question. Okay. So basically, the neutron beta decay process, there is with respect to, basically it's given in terms of quarks basically. We will come back a little later. So this is the beta decay process can be carried out in all topics, let's say from the elements, nuclear aspect, and then nucleon aspect, and then quark aspect. Okay, in all three aspects you can discuss. Okay. So let's talk about something else further. So in the category of the category of these, there is something called muon decay. Let's say first we have discussed beta decay. There is something called muon decay. The muon decay and two photon decay. So two photon or pion decay. So let's say the muon decay. So muon. So basically, this is one of the elemental particles. It's a mu minus. It goes to the electron plus the neutrino plus mu. So basically, this whenever there is this mu is a kind of another elemental particle, comes under electronic particle. We will classify all of them, but this decay looks like this. If you put this mu minus, when the electron comes, there is anti-neutrino. Similarly, anti-neutrino mu1 comes. Okay? And similarly, the pion decay, let's say, or if it is a mu plus, it will be something like a positron plus neutrino plus mu bar. Okay? So, and then pion decay. So this pi plus goes to mu plus mu. Pi minus goes to mu minus plus mu minus. And the pi 0 goes to gamma plus 1. And this is called the 2 gamma transition. Okay? So we can say that 2 gamma we say that it's a 2 gamma transition, either pi 0 or neutral elemental particles will convert into gamma transitions. Okay, and so the neutral pions, neutral eta. Not only this, you will also get eta 0, and it goes to gamma plus gamma. And then we also have bosons, scalar bosons, H naught goes to gamma plus gamma. So these are two possibilities. And the pair production, let's say electron plus positron, also you can give this gamma plus gamma. Okay, so pair production, this is pair production. Okay, so let's say. So basically, you need, let's say, these are bosons. So bosons are demanded for 2 photon decay process. And these 2 photon, the moment you have photon, electromagnetic interaction. It comes under the type of electromagnetic interaction. Probably I'll discuss in little detail in the case of elementary particle aspect. Before going into this, maybe you write down this relation. We'll come back here, and one particular problem that I was talking about from Devanand and Sir group, so we'll discuss that. So problem number 33. We'll come back to why. So this is one of the straightforward problem. Let's say if it has 2 gamma emission, the particle must be a boson. Yeah, all the bosons, most particles will convert into 2 gamma photons. So there is the take home message here. And the process which involves is electromagnetic interaction. Now, the 33rd problem is also so 4 MeV gamma emitted by the de-excitation of fluorine 90 are attributed, assuming spherical symmetry, to the transition of photon from 1D 3 by 2 to 1D 5 by 2. So this is the problem. So when this fluorine atom is de-excited from 1D 3 by 2 to 1D 5 by 2. 1D 3 by 2 is N minus S, it's in a higher energy. D 5 by 2 is a low energy state. So when it comes from high energy state to low energy state, this 4 MeV gamma ray is being emitted. If the contribution of spin orbit term to the total energy is written as C times expectation value of N dot S. The moment you see here, it's an expectation value bracket. The magnitude of C is, so that's what the question is. Okay. So this is your delta E, and the transition is this. The question asked is for these methods. So first of all, we should know the expectation value of L dot S. So basically, expectation is nothing but the average value. So average value for L dot S, whenever you see such thing, it's always 1 by 2 times J square minus L square minus S square. The J square can be written as J into J plus 1 minus L into L plus 1 minus S into S plus 1. So basically, when J square operator acting on a state, what you get the eigenvalue is J into J plus 1. So that's why it is J into J plus 1. So this J is what the spin. So what we need to do is, we need to find out for this particular term, the spin value is off. What is any value? 2. Is that correct? Because it's a d orbital. And what is the J value? 3 by 2. So we need to find out for this one, what is the L dot S term. We need to find out this similarly, what is the L dot S term for this expectation value. Okay, and then you need to subtract the difference in the L dot S value. So your delta E is C L dot S for the 3 by 2 minus C times L dot S for 5 by 2. So when you take the difference, you will get the common factor C. Yeah? So this is the approach, and you know that delta E is given. So delta E is your C L dot S expectation value of 3 by 2 minus C L dot S expectation value of 5 by 2. So will you do this from you to make these values, and the C answer C should be 8 by 5. 8 by 5 in terms of MeV. I'll just come back in 5 minutes. Okay? You got the energy difference that goes down. Is that minus? Is that okay? So that's okay, but this is how you calculate this kind of problem. And this problem is exactly available in the Devanagari circle with 5 MeV value. Okay. 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 Now let's move on to the. So you all studied the elementary particle, right? And the classification. So So basically the elementary particles are classified based on the interactions, based on the spin, and based on the what do you call this? Yeah, these are the major types. So let's say so based on the spin, the elementary particle. So based on the spin value, whether it is a half integral or I call this Febvre and an integral spin. We call them as bosons. The examples bosons, photons basically. Then again, it's bosons. It's a meson. Mesons, correct? The mesons are called pi and k mesons. Major. Okay. So pi and k meson. And the fermions, you will have basically you will have leptons, then baryons, hadrons. These are all like kind of integrals in values. So basically the leptons, baryons and hadrons are called let's say the baryons the leptons are, let's say you have this electron, neutrino, antineutrino, positron, neutrino. Normally let's say the mu and then mu. Let's not worry about this antiparticle and tau and mu tau. So these are all called leptons. Okay. So electron, mu electron, tau electron. You can say electron itself. A tau particle, mu particle. And their antiparticles are positron, mu, and you see this is minus sign here. Minus and minus. Then plus will be like antiparticle. Neutrino respectively antineutrinos. And then baryons are neutron and proton. And hadrons comes under, let's say, your hadrons are, you have lambda, sigma, and then you have a xi. So you have plus minus is there, plus minus, and then 0. So all three possibilities are there. So these are called hadrons. And based on the interaction, let's say based on the spin, based on the interaction, so you have strong interaction, weak interaction, and electromagnetism. So these are three types of interactions. Okay. So the strong, electromagnetic, and weak, all three are satisfied by, let's say, the hadrons. And that consists of mesons, baryons, and the hadrons. So either you commonly call them hadrons that consist of mesons. These are bosons, and these two are fermions. So all these three satisfies or involves in all possible interactions. Okay. But whereas leptons are only with respect to the electromagnetic and weak interaction. So leptons comes under either a weak interaction or electromagnetic. So only these two will be important. Okay. So leptons basically only these six elements and their respective what do you call it, antiparticles. Okay. And then the the conservations, basically the conservation that involves a lot of conservations. Let's put this. Let me brief this and then we will try to solve it. So let's say you have conservation and the interaction, let's say strong interaction, then weak and electromagnetic. Okay, classify them. So let's say mass, energy, mass or energy. Conservation. With respect to these, all of them can be involved. So everything must satisfy, whether it is a strong interaction, mass energy, mass conservation, energy conservation. That should be there. And then the proton number is stands for okay, momentum, let's say. Momentum, angular momentum, and then charge value, baryon number, electron, electron number. So up to this all of them must satisfy. Up to this, all of them must satisfy. So whereas this isospin value, isospin is nothing but the third component of the angular momentum. Your angular momentum, let's say if you have this G, the third component is basically mg. Okay, so for a given j value, your mj will be 2j plus 1 number of times. For example, j equal to 1. The mj can have to plus 1, 0 or minus 1. So basically it's a cone. Imagine there is a cone that is moving like this. That means it is a one orbit. It occupies, it's basically, this is nothing but the spatial quantization. Your spatial is being quantized in terms of z-axis with respect to the magnetic field. Either here, if you, the next layer is in the surface, or in the bottom. These are the only three energy levels are allowed. In between, there is no values. So we call this a spatial quantization. Okay. And similarly, this isospin is the third component of the angular momentum, I3. And this I3 will be satisfied only for the strong. Whereas in the case of weak and electromagnet, it's not going to be conserved in the sense. This is the conservation clause. Okay. And the strangeness is defined as something like kind of based on the quantum number. Okay, strangeness. This is a behavior, and the strangeness is being satisfied for these and these not for these. And then a hypercharge. It's called the Y. And this Y is being related as B plus S. So this is the very basic relation. B is the barrier number, S is the strangeness number. So the strong interaction do conserve, whereas electromagnetic do conserve. And the last one, the parity. So the parity is these, not these, these. So these are the laws of conservations. Okay. So the classification and the laws of conservation. And this classification can be grouped then as a kind of octet. We heard this meson octet, baryon octet. Anyone can draw it? One of you can. Sorry, put the Bangla class. Yes. Yes, sorry, put the So basically the meson aspect. So the meson octet is being drawn between the y and I3 and y equal to b plus s. In the case of meson, meson is a bosons. Okay? So mesons are part of the bosons, Bose particle. There is no barrier number. It's only hadron, comes under hadron. So therefore this is 0. In this case your y equal to s. Right? And then you have, let's say, hexagon or octet, because you have 8 corners. 8 particles will be put here. And let's say, to simply remember, you must know this pi plus, pi 0, and then pi minus. And there is a k meson, pi meson and k meson. The k meson, let's say this is a k plus, then k minus or k minus bottom. K minus bottom. And this is k0 bar and this is k0. So this value is basically 0, this horizontal. And this one is a minus 1 and this is a plus 1. So that's how it is a strange number and hypercharge are equal in this meson case. And also you have one more particle called eta naught. Okay. So yes. So yes, also.
So 6 no is
right, 6 corner and then octet the period. Okay. So then this I3 value, basically this is 0. And then this point is basically 1 by 2 and this is plus 1. Minus 1 by 2 and minus 1. So now I mean the serial polar. This exact time in the point in the value. Okay. So symmetry is very not but that's okay. So therefore if someone asks and the charge value from here you can get the information charge. So let's say pi plus is a plus charge, neutral negative charge, k minus negative, k0 bar is a plus charge, and this is a plus charge and this is a neutral. So in a sense you get a charge value and then this charge value q can be defined as I3 by 2, let's say I3 plus y by 2. So that is what is charge for every aspect. So let's say your I3 is, this one is 1 and y value is 0, 0 by 2. So it is a plus 1. Okay. So for this one, what would be the charge? Your I3 is 1 by 2, y value is minus. So 1 by 2 minus 1 by 2, it's 0. Okay. So the q and y relation, you get a q value, you get an isospin number, and you get a y value. All the information in one package. Okay. And correspondingly, you can also draw in terms of quark values, but that we will do it later if required. And then the baryon. For the baryon, again you have octet, something like this. So again you have y and then I3. And again you have, in this one, the baryon, therefore it's a proton and neutron, and you have a sigma class, sigma 0, lambda 0, sigma minus, and then you have chi minus, chi 0. So basically chi, you have to pronounce this as a chi. Okay, capital chi. So chi 0, chi minus. Okay. So again same thing, the baryon number is 1 for this. So your y equal to b plus s. Therefore the strangeness will be minus 1 of this value. So this is a plus 1, 0, minus 1. For neutron and proton, baryon number is 1, y is also 1. Therefore, the strangeness 1 minus 1. It comes to exactly this goes down little lower. Okay. So these are some basics that we should know. And the quark values, the quarks are made up of, let's say, 3 quark and then 2 quarks. So the pions, there is one more like baryon. Okay, thank you. In a baryon, there is one more like a 3 by 2 particle. So I hope you might know. So baryon of 3 by 2. DQ plate. DCUP, CUP. DQP. So basically, it is something like this. So you have omega, and this value is omega minus, and this y value is minus 2, and this one is I3 value. So you have chi minus, chi 0, and you also have sigma plus, sigma 0, sigma minus. So this one is minus 1, 0, and this is a plus 1. This is y value, y. And this one is, let's say, delta minus, and you have delta 0, and then you have delta plus, delta plus plus. Okay. So basically, this is another kind of classification. So basically, this value is 1 by 2, comma, minus 1. So 1 by 2 is this I3 value, and 0 for this 0, comma, minus 2, I3 value. And here I3 value is, let's say this is 1 and 0. Okay. And this one, 2, comma, 0. So you have a 2, 1, and then minus 1, minus 2, I3.